Hello and welcome to the second session of our workshop series, Applications of CFD in Formula Student and Formula SAE, by SimScale in collaboration with Formula Student Germany. My name is Milad, I'm the Product Marketing Manager here at SimScale, and as part of my role, I'm organizing webinars and workshops about different topics to introduce new users to the world of engineering and engineering simulation. However, before I joined SimScale, I've worked in other industries, including motorsports, and there I was working at the World Rally Championship team and for a F1 team in the field of aerodynamics and CFD. And yeah, today I'm going to be your host and presenter. And first of all, let's take a quick look at our agenda. Since this is the second session, there was some confusion about the date of the first one. I will quickly, less than 3 minutes, summarize the most important organizational things at the beginning, and then we will start to dive into our today's topic. So today we will talk a lot about CFD. So we will start to discuss about some fundamentals, what CFD actually is, how it's working, and then we will also talk about some important aspects and some techniques which we use to model flow features which are present at the Formula racing car. And after we've talked about the basics, we will take a look at what we call a live demo. So we have prepared a simulation of a Formula student car. It's a half car, including radiators, wheels, etc. And we will show you how to set up the simulation, what the things we have taught you before, how they are related to the simulation, and in the end we will drive through to the results and discuss them together. Yeah, some organizational things. So as I mentioned, the idea of this workshop is to introduce new and interested users from the field of Formula Student or Formula SAE to the world of CFD, and to enable them to develop their own CFD methodology and to develop their car using it. And this course is actually made out of 4 webinars, and during this webinars we will discuss the whole curriculum of the course, and after the last session at the end of this month we will send around a voluntary homework quiz, and if you answer all the questions correctly, you will receive a certification. And the great thing is that we will also provide you with resources and tutorials so that you can also run simulations on your own. And all participants will get free access to the SimScale platform, and you don't need any prior knowledge, soft or hardware, to take part at this webinar series. Yeah, let's just take a look at the course curriculum. So last week we started with Introduction to Aerodynamics, which was held by René Hilhorst, who is a CFD Aero veteran. He was the head of aerodynamics at Toyota F1 and designed the very first Toyota F1 car more than 10 years ago. And yes, he shared a lot of knowledge with you about really the basics of aerodynamics, starting from what is a fluid. We talked about boundary layer, and later about wings, wing theory, and how wings are used at race cars. As I mentioned, today we will mainly talk about CFD and how we simulate the aerodynamics of a full car. And this is, let's say, the fundamentum, the second part of the fundamentum, which we need for the next 2 sessions. So in the case you have missed the first session, or you are watching the recording now, please make sure that you really understood everything discussed in session 1 and 2, because next week Tommy Lasso will joining. He was the former head of CFD at Ferrari, BMW Sauber, and Sauber. And starting from next week, we will start to talk about more hands-on aspects of CFD and more about how to use it as a tool, while today we will more try to understand what CFD is and how we can use it. Yes, finally, we are going to record the sessions, and we will provide you with a link to the recording probably tomorrow or beginning of next week. And if you've got trouble with setting up our own simulation, or if you have questions related to the course, we offer free support through our forum. On simscale.com/forum, we have our own category called Formula Student Workshop 2018, and there you can ask all your questions. And finally, there's also the opportunity to become sponsored by SimScale. And we actually sponsor every official registered Formula Student team. You just need to download and fill out and submit our sponsorship application form. And every team can register once, and you will receive one team account, access to unlimited private projects and call hours, and access to exclusive tools and exclusive webinars, as well as free premium chat. Yeah, all right, and now we can start to dive into our today's topic. In the case you have questions, please write them into the question toolbox like Edwin did, and I will try to answer these questions on the fly or latest during the Q&A. And so the first question was by Edwin, if we can share the slides from the last webinar. Edwin, unfortunately, this is not possible since we not own the copyright on all of the materials, and therefore we are not allowed to share them with other parties. Sorry. However, if you know, there are some tools and it's on YouTube, so you will actually still get access to the slides. Yeah. Now let's start to talk about CFD. And as I mentioned, first of all, I would like you to understand what CFD actually is. And I know that this is sometimes very hard, and some of you maybe don't have the, you know, the best, are not remembering the best moments of their studies when they try to understand something like this. So let's try to make it easy and to understand step by step what CFD actually is, how it's working, and yeah, so let's start. And yeah, first of all, what is CFD? So CFD is a acronym. It stands for Computational Fluid Dynamics. And this can be translated somehow into virtual wind tunnel or fluid flow simulation. And the idea of CFD is pretty simple. And to understand it, we have to, you know, take a look back 200 years, 300 years ago. And back then, two scientists, or several scientists, simultaneously found out about the equation which we know today as the Navier-Stokes equation. And this is an equation or a set of partial differential equations which are describing, let's say, the conservation of different quantities inside a fluid flow. And there's some good and some bad news. The good news are that this equation, where, as I mentioned, developed like several hundred years ago, so they're existing for a very long time. And we are quite sure that the equations are correct. The big problem is that we have the equations, but another thing we know is that they are not solvable, so we cannot solve them analytically. And this is actually where CFD was born. And the idea behind CFD is very simple. We have these equations which are describing the conservation of mass, momentum, and energy. We cannot apply them on complex geometries, and we cannot solve them for complex geometries. So what we do instead is dividing our model into small, what we call cells or elements. And then we can like recompose our complex model from these simple elements. And for the simple elements, we can easily apply the conservation laws. And in this case, the very simple case, we just need conservation of mass and momentum if we assume that it's an isothermal flow. And then the idea of this Navier-Stokes equation is nothing more or less than that the rate of mass change inside the cell is equivalent to the inlet mass flux minus the outgoing mass flux, so the outlet mass flux, and actually the same for the momentum. And so what we do is, and let's say we want to simulate the flow around such a multi-element wing assembly. First of all, we divide our problem into a lot of small sub-problems, which are made of these regular shapes. And now the magic starts. Okay, so what did we gain so far? Well, first of all, we are able to describe this problem. With the wing geometry, it was not very easy because it's an irregular geometry. But in this case, now we can describe, based on this cell structure, the problem of the flow around the wing. But still, we cannot solve it. And to be able to solve it, we will use another very old law, which is called the divergence theorem. And some of you who've studied maybe electrical engineering also know it, because it's also very important for the Maxwell equations. In the end of the day, this divergence theorem or Gauss theorem says nothing more or less that there is a defined relationship between what is happening inside a closed domain and what is happening at its boundaries. And it allows us to calculate phase values in terms of cell-centered values. And the cell-centered value is representing everything inside the cell, while the phases are just representing the mass flux through the boundary. And keeping this in mind, this will allow us to transfer our analytical problem into a numerical problem. And this can be done by integrating over the cell, because applying this divergence law in the first step allows us to describe what is happening inside the cell due to what is happening at the boundaries and the other way around. And in the next step, if we now integrate our partial differential equations, which we've transformed before using this Gauss theorem, our analytical problem where we have derivatives inside the equation will be transformed into a linear equation system. And this is a big difference between, because a PDE, this one, I simply cannot solve it. But if I know a solution, and I can test it if it's the right solution, and in contrast to that, a linear equation system, it's a numerical problem. It's not precise anymore, because in the end of the day we did some mathematical simplifications. But the big difference is that now I'm not looking anymore for, let's say, infinite number of velocity pressure values inside my domain. No, but I'm looking only for the cell-centered values, and based on them I can calculate everything else. And this is my real linear equation system, which I can solve directly or numerically. And this is maybe the final important step. And now I need to solve this linear equation system, which can be very hard, as we know, because it's usually so big that you can't use the standard procedures we know. So we use numerical methods, which are able to solve basically any linear equation system as long as it's solvable, and that's the case. And that's why we're doing it yet. And this is what most of you know as CFD, because this is a process of iteration. So we will start with a solution, an initial solution. Then we can calculate the residuals, the error, and based on that we will use other values for our degrees of freedom and calculate it again. And this is like an iterative recursive process. And in the end of the day, this allows us to represent our flow phenomena. And yeah, this is basically the idea of CFD. So to put it in a nutshell and to explain in a very unscientific way, it's what you're doing in the end is that you are discretizing a problem. And since we are not able to calculate an infinite accurate solution, we will calculate a numerical one. Yeah, okay. And now let's talk about the main components of a CFD simulation, in the case there are no questions in the meantime. So if you have questions related to this part of the presentation, please ask them now, because it would be a shame if yeah, we have to start again in 30 minutes to talk about the very fundamentals. Okay, seems like everything is clear, so let's continue. And on the slide right now, you can see the 6 most important components of a CFD simulation. And just to make sure everybody is aware of that, if you ask maybe another CFD engineer or your professor, he will write down maybe some 6 other terms, or 7 terms, or 8 terms, or only 5. And in the end of the day, this whole topic of CFD numerical engineering is very complex, and therefore it's very easy to get confused by a synonym or something like that. So be careful. And here you can see, as I mentioned, the 6 most important aspects, and I would like to discuss all of the aspects there with you. And let's start with what we call mesh. Well, as I told you, it's necessary to divide our problem and to replace this single domain by a model which consists out of a lot of small regular shaped cells. And this process is called meshing. And with this process, or inside this process, we are actually defining our local accuracy for a flow simulation. And just think about it. You will only calculate for every cell center velocity and pressure, which means if you have high gradients, you need more of a finer mesh, and where you don't have so high gradients, you can use a coarser mesh. And meshing actually is the biggest bottleneck in CFD. And usually it takes like 70% of your time. And SimScale is using a tool or a toolbox called OpenFOAM in the background for meshing and CFD calculations. And OpenFOAM is also used in F1 by several teams. I'm quite sure they modify it, but the great thing about OpenFOAM and SnapPX Mesh is that it has a completely different approach on meshing. Usually it's a bottom-up approach, which means you need to smash first edges, faces, surfaces, volumes, and so on. This time, you actually start with the background mesh, and you just define local refinements. And let's go through the process. So if this is our car, the first step we need to do is to create a background domain. Since we're interested in the air which is flowing between the car and the ambient and not what is happening inside the car. So we have two geometries. One is the car, which needs to be a closed model, because otherwise we have holes where air will get into the car, and we have the background domain, which will represent, in the end of the day, our wind tunnel box. The first step is called background meshing, and there we actually create, and this is very easy, we'll create an automatic background mesh, which is very coarse. And right now, this background mesh is actually not helping because it's just like a rectangular pipe, which was very coarse. But what we do now is, based on your user settings, you can define different refinements for edges, like here, for whole surfaces. And once this is done, and you've applied all your refinements, the meshing tool is like intersecting your geometry with the background mesh and deleting the inner part. And this is maybe the first or the most important step, because now a flow around or flow inside the rectangular pipe or tunnel becomes the flow around the car. Still, we can notice some things. First of all, our mesh has this, it looks very steppy, so it's, how should I say, it looks like a Cartesian mesh. It's not smooth. And we don't have any volume refinement. That's what we're doing next. First of all, we apply what is called a volume refinement. And in contrast to all the other refinements, this refinement is not only applied on cells, background cells in the near of the object, but you can define it for closed volumes everywhere inside your domain. And the final step is called snapping. And this is where we are projecting our elements back to the surface, and this makes the mesh smooth. And this process looks very simple, it actually is, as long as you're following some important guidelines and as long as the geometry you're uploading is properly prepared. But this is something we will discuss during the last session in 2 weeks. Now, and once snapping is finished, there's an additional optional process step, which we really recommend to do. Without it, your CFD results for turbulent flow will be crap, and this is called layer elements. And these layer elements, if you take a look at the screen, they are actually very flat. And now let's try to understand why we need them. And therefore I prepared a slide. And this topic is very much related to something we call wall modeling. So what is wall modeling? Well, as you can remember from last week, where René explains that there's a boundary layer where viscous effects are dominating, and there is an outer layer where we can actually neglect viscous effect. And the big difference between them is that inside the boundary layer, since we have this viscous effects, the flow speed is lower than the inflow speed, or the speed at the inlet. And there are different criteria. Usually say around, if it's lower than 99.8% of the free stream velocity, it's part of the boundary layer. And you maybe also remember that inside this boundary layer I have a very high gradient because the fluid actually directly on the wall, there we have a sticking condition, so the velocity, no slip condition, the velocity itself is 0 meters per second in all three directions on the surface. At the outflow, it's like the let's say 20-30 meters per second. In between we have a profile which is not linear, and it's actually looking like this. And this is our boundary layer profile. And if you now take a look, the spatial change in y direction, in this direction, is very high, very high. But in this direction, so if you compare this and this vector, there is a huge difference. If you compare this and this vector, it's quite small. And that's a problem. A lot of our global flow characteristics are dictated by what is happening inside the boundary layer. Therefore, you need to properly solve it. But if you would now use our standard hexahedral elements, we would need 10 or 20 times more cells. A lot of them are wasted because we just want to resolve an gradient in x direction. So instead we use these flat cells, which allow us to save a lot of cells. And it's important to apply them on all physical walls for turbulent flows. And it's also very important to never apply them, really never, on non-physical walls, like inlets and outlets, because this will create a lot of problems. Because then it's exactly the other way around, and then it will definitely make a simulation crash. And it's even a little bit more complex. And therefore, let's talk a little bit about the law of the wall. So the law of the wall is also like 100 years old, and actually it's nothing more or less than a description of a relationship between the dimensionless velocity and the dimensionless wall distance for a turbulent flow. So really, the big idea here is that independent from the flow physics, so independent from the application, if it's a car or an airplane, at the end of the day, in every turbulent flow, I can find a relationship between the dimensionless velocity and the dimensionless wall distance. Just in the case some of you don't know what dimensionless means, it actually means that you divide your velocity. You make it like, yeah, as it's dimensionless. So it's important because you are not interested in absolute values, but in relative ones. Well, and the great thing about this law of the wall is that if we take a look now on the right side, here on this slide we can see how this profile is looking like. And we see that we actually have three layers. We have what we call the viscous sublayer, and it's defined from 0 up to a y plus value of 1 to around 3.5. Then we have the buffer layer, which is from 3 to 10, 110, 120, and we have the log law layer, which is going from 120 to 300. And what I can do now is, instead of resolving, let's do a stop here first of all, because this is very important. So there are two aspects of wall modeling. The first one is that I need to properly resolve the boundary layer. And usually this would mean I need to spend a lot of cells there. And another aspect is, and that's another important point, instead of like using 10 to 20 layer cells here, if I take a look, it seems like that it's a logarithmic relationship here. And so what I can do is describing this whole part of the curve just by one constant rise or slope here. And in the end of the day, it allows me to include the whole viscous sublayer of my simulation into the first cell. And instead of modeling, and then it allows us to model the velocity profile based on this law of wall, instead of calculating it. And that saves a lot of cells and computing time. But this requires a decent or a value for y plus inside the first cells. And if you don't use wall functions, your y plus needs to be 1, and if you use wall functions, you can also have higher y pluses, because then it just needs to be somewhere here in between. Yeah, and usually when we do CFD simulations, we suggest to use wall functions and really make sure that your boundary layer mesh is looking fine. Well, we've talked about meshing. Now the next step, or next two things, are initial and boundary conditions. I don't want to talk too much about it, but listen. So, if you remember what I told you about the CFD process, and that I have this linear equation system, which I can solve now using numerical algorithms or numerical schemes. As you know, for most of numerical schemes, I need starting values, and this is what is called initial value. So you need, at the end of the day, you need for every of your cells a starting value to calculate the first residual and then to calculate the next solution. And this initial conditions or initial values or initial state, it is not the most important aspect. And I could talk for hours about it, but let's make it simple. So, in the end of the day, if you take a look at this from a hands-on perspective, initial conditions, usually you never need to touch them. And it's like this. As more your initial conditions are in the near of the solution, as faster your simulation will converge. So this process of reiteration will become shorter. But it's not very easy to find the right initial conditions. Therefore, usually what we do is we initialize everything with 0 except of the velocity and pressure, which are initialized using a potential flow approach. But this is something we'll also talk about more next week. But remember, initial values, every time you do this for CFD, for Racecar, use potential flow to initialize. And in contrast to initial values, boundary conditions or boundary values are not describing the initial state of your system because, let's take a pen. Initial values are like for your whole domain. And only for the beginning of your simulation. This is, by the way, not necessarily physical time, while boundary conditions are only for the boundaries, but they are valid all time. Yes, also very important aspects is the choice of the right numerical settings. Since we're using numerical schemes and numerical math to solve these problems, and all those algorithms have some settings. And some of them are simple to understand. For example, relaxations are controlling how aggressively you are changing your next results for the iteration. But there are some other which are more complex to understand. And this is something we won't talk too much in detail about because, you know, it's not like that you can understand half of it. You really need to take time if you really want to understand what is happening here. But as I mentioned, we will provide you with standard settings, which should work very well for every Formula Student Racecar simulation. Then there is something else which is much more important, turbulence modeling. And this is something we need to talk about again. So, what is turbulence, first of all? Turbulence is defined as a chaotic change of field values in space and time. So it means if you put the pressure probe or pressure sensor into a turbulent flow, you will see that even if the pressure seems to be constant, it's fluctuating all the time. And a very good example to understand what turbulence is depending on and also to be able to control it yourself is using a water tap. Use a water tap, open it a little bit. You will see, first of all, the flow looks very regular, and if you increase it more at some point, it will become to look chaotic, and the phase boundary starts to look different, and that's when your flow becomes turbulent because your Reynolds number is too high. So flow becomes turbulent if the Reynolds number is too high, and the Reynolds number is the ratio between the viscous and other forces. And if you now take a look at the graph on the left side, let's say this is representing the velocity value somewhere around our car. And we are driving in a perfect wind tunnel with a perfect constant airflow. And if we measure it, we will see that, well, this value is fluctuating all the time. And this is a big problem because we are not, because that really would need to calculate every simulation fully transient with very small time steps. Because this, how should I say, these oscillations can happen on very different time scales. So the time scale, and this is also a question which is asked every year. So what is a turbulent time scale? Well, in this case, this would be a large time scale, and this would be a small time scale. It's not as easy every time, but it's about like which is typical time a process is happening in. And since since usually you have a high bandwidth of different time lengths, it would become a big problem if you would really try to calculate the turbulent flow around a Formula 1 car. Actually, I would say it's not possible. And therefore, what you do is using a turbulence model. And here the approach is very easy. So the first idea we have is, well, what if I average my flow or my quantity, and then I can replace it by the average value plus a function which is representing the oscillation, this one. And then I actually just need two values. But I have a problem because, wait a second. And since we are not able to solve, what we will do is that we replace the oscillations, because just to get it right, U plus, these oscillations are very small. And so what we do is that we neglect them in the first step. But then we have a problem because now our equation system is not closed anymore. And to close it, we will introduce just a new artificial quantity called turbulent viscosity. And just to make it clear, the turbulent viscosity has no physical meaning. There is no turbulent viscosity of a fluid. It's just an artificial quantity we have introduced to be able to close our problem after neglecting the oscillations. And what we're doing now is, and that's very smart, instead of calculating the oscillations, we just need to calculate the turbulence viscosity, and then the turbulence viscosity is added to the physical viscosity, and this new effective viscosity is then used for the momentum equation. And so we close our equation system again. And now we can calculate the turbulence based on additional transfer properties, artificial transfer properties. Most of them are called turbulence intensity and turbulence dissipation rate. And we don't need to solve anything for all time and length scales. But listen, and this is really important, this is a major simplification. And whenever you do turbulence modeling, you need to be aware of it. And it's very easy to take the wrong conclusions. Yes, and there are a lot of turbulence models. For this webinar, or in general, I recommend with OpenFOAM and SimScale to use the K-omega SST model only for external aerodynamics. The reason is that all these turbulence models were created for different applications. There are turbulence models which are very strong for the flow in the near of walls. For example, the K-epsilon omega model, but there are other models which are very strong calculating the turbulent dissipation in the free stream. And the K-omega SST model is basically combining best of two worlds, because it's automatically switched between a K and epsilon and K-omega formulation wherever necessary. So in the near of the world, it will use the K-omega and the specific dissipation rate. and far away from the wall it will use the turbulence dissipation rate. And these are just different quantities which are used in the end of the day to calculate your turbulent viscosity. And since I was talking about this time and length scales, this image on the left side, I think it's visualizing pretty what is happening. So I have energy cascades, and big vortices are falling into smaller and they into smaller ones, and so energy becomes dissipated over line time scales very slowly. Well, and now there is a last part. We talked about meshing, initial boundary conditions, numerics, and turbulence modeling, and now I would like to talk about everything which do not belong to one of the other categories, and so I will call all of them solver related. And now we will talk about additional models which we not need for CFD in general, but in our case to simulate the flow around the car. And when it comes to a Formula race car, there are a lot of things we need to simplify. And there are some things we cannot simplify. And one of the things we really need to consider is the flow through the radiators, or let's say the internal flow of the car. And again, we will use a model which is simplifying everything, because if you think about it, if you would like to simulate really the flow inside a radiator, you would need a super high mesh for the radiator, because this is the radiator can be very small, or the elements can be very small, and this is not an option, because then you would end up with, I don't know, double or 3 times of elements for a simulation. It would take much longer, and at the same time it wouldn't add a lot of value. So we do something else, and we use the Darcy law and use the porous media formulation to model the effect of the radiator. And actually Darcy's law is describing the pressure drop when a fluid is streaming through a porous medium. And this pressure drop is represented as the quadratic function, which is dependent from 2 parameters A and B, and from the mass flow rate through the porous medium. And in the end of the day, what we do is that we characterize our radiator and replace it with a new volume. And there we describe, let's say, the resistance in all 3 directions. And in the end of the day, we just need to provide then some transport coefficients for all 3 axes. And the great thing is that later we don't need to create any additional mesh. We will just create a standard mesh, define all the cells inside the cell zone as a porous media, and then they will act like a radiator. And on the left side you can see the visualization of the Darcy law for a race car radiator. So you can see for different mass flow rates how big the pressure drop is. And another point which is very important is what we call wheel modeling. So if you think about it, actually in reality it's not like the air is streaming around your car, but your car is driving through the air. So it means that our wheels and the car itself have a relative velocity compared to the floor. And there are 2 effects we need to model. The first effect is that the wheels themselves are rotating, so we have a wall velocity on them, which is depending on the distance from the axis. And the other is that actually the rims themselves, since they're rotating, they're working like a pump. And since our mesh is not rotating, we need to find other ways to model this. And therefore we'll use 2 things, rotating wheels and MRF. Rotating wheels is quite simple. We just apply rotational velocity on the wheels and the tires and the rims. And MRF stands for multiple reference frame, and this is a technique which allows us to virtually rotate, let's say, parts of the mesh. And in the table on the left side you can see simulation, and the only things we change is if the wheels are rotating or not, or if MRF was activated or not. And you can see like how big the influence is, that the front and rear wheel lift and drag values are massively changing depending on how we model it. Yeah, and now it's time for our live demo, and therefore I will switch now to the SimScale platform. I've prepared a CFD project for this, everything I'm doing here is in the web browser. Now let's first of all open the model. Okay, now we're inside the platform. First of all, let's take a look at the geometry. So this is the CAD model of our car. As you can see, it's a half car model and it's watertight. That is very important. And also, we'll talk about it in 2 weeks again, but that you have a good and logical structure of your model so that you can change parts and also analyze different parts. And you can upload your model using different file formats, including CATIA and SolidWorks. But we suggest or recommend to use the STL file because there you have the most control over your geometry. And the next step is to create the mesh. And therefore you need first of all to select your domain. Oh, sorry. For the mesh, it's here. We have a lot of settings, as I mentioned. You have also automatic mesher, but you know it's not as powerful as manual meshing. And as you see, as I described here, you define the bounding box resolution. And then you can define different refinements. And every refinement level means the cells will be split once. Once you've defined the mesh, by the way, I can show you how to create the MRF zone. So for the MRF zones, as well for the radiator, for the porous zone, we need to create a cell zone, which we're not doing with the others. And I can show it here how the cell zones are looking like. So we have MRF, MRF, and radiator. And if we now hide everything else, these are the dummies for the MRF cell zones and the radiator cell zones. Yeah, once the meshing is finished, the next step is to set up the actual simulation. And I will not, just because some people were asking, based on our experience from the last 2 years, we will not show you in detail how to set up the simulation because we will provide you with the projects and tutorials. So you don't need to write something down to do it on your own. Just watch it to get a little bit of feeling for the platform. And if you have questions, then use our forum. Yeah, and the next step is simulation. So you choose a mesh, you choose the material for your wind tunnel. In our case, it's air, and we can import the material properties from a library. And then you define the boundary conditions. We will discuss about the boundary conditions in some seconds. I just want to show you one thing. It's that once everything is set up, you can run the simulation. This takes some hours. And once this is finished, you have access to all the force values. For example, these are the forces acting on the body of the car, different directions. But you can also get a look at the 3D results. And this, by the way, to load this full car can take up to 5 minutes, since it's a lot of data. In the meantime, I will answer some questions. So Henrik wants to know if the resolution of the mesh is fixed or adaptive. Right now it is adaptive. So in terms of it's not changing during the computation process or the solving process. Yeah, but we are working on it, and there will be soon a feature available for adaptive meshing. But from our experience, also not necessary. Okay, and the next question is by Konstantinos. He wants to know why using a wall velocity on the rims is not enough for wheel modeling. Good question, Konstantinos. We will discuss it in 5 minutes. Well, so I've loaded the results. First of all, we can like load the model. This is now an outline representation. We can also change it to surface outline mesh or change the color, you know, what you like. And now let's create a cutting plane. I would say in y direction. And we'll visualize the velocity magnitude. And now we can like move the slice, analyze different parts. And there's a lot of more you can do. And if you want to learn more about manual post-processing, we have a webinar recording, Post-Processing with Peer Review for Formula Student, which I recommend to take a look at. However, now let's continue with the presentation. And so one thing I would like to do with you now is to discuss the boundary conditions, just to understand what we actually did. And therefore I've used different colors. And as you remember, I told you the boundary conditions are values at the boundary of your model which will never change, which you know. And in this, I hope with this example some things will become more clear. And so let's just start, and if you have questions, just write a comment. So where's my key? Well, I don't know how the flow field at, let's say, 20 meters per second will look like around the car. But there are some things I definitely know. And one is that if the inlet velocity is 20 meters per second, that on this red surface, the velocity value or the velocity vector is looking like this for every cell. No discussion. The same with the car. Since the car is a wall, except the wheels, it will be 0, 0, 0, our slip condition. The floor. We have no relative velocity between air and floor. Don't forget, the car is driving through the air, not the other way around. So they necessarily need to have the same velocity vector. And yeah, then, you know, for the symmetry, we know that the gradient of U needs to be 0. For the outlet, we know the pressure will be, let's say, 1 bar. And in the end of the day, for every of the faces, for every boundary faces, at least there are, you know, we have velocity, pressure, and at least one of the values for every phase we know, the other one we want to calculate. And this is how you define your boundary conditions. Yeah. Just to talk about the process. So the first step is to import your model, what is called pre-processing. Then you create the mesh, set up the simulation, so define the boundary conditions, models you want to use, etc. And the final step is doing the post-processing. And yeah, just to, in the case, because some people asked, so during the meshing, the first step is to create and open a project, choose hex-dominant parametric meshing. It's important to use layer elements and to create cell zones. For the simulation setup, first of all, you use general setup, the mesh assignment, you define the material, initial and boundary conditions, then you can start to run your simulation. And post-processing can be done online as well as offline. And yeah, as I mentioned, last year we showed in detail how to do it, but since we now have a very long video about post-processing, I would suggest to take a look at this. Well, and now let's take a look at some of the results and answer some questions. So this is the first result. This is the total pressure field which is created, and now this slice is moving through the car. And Torbjörn will talk with you about how to use this total pressure field. But this is, I would say, the most important field that you will need for post-processing, even more important than velocity. Why? Because total pressure includes information about both velocity as well as pressure. And the animation is quite quick, but we can already see how the wake is formed behind the car. And now let's try to get some information out of the results. And first of all, let's just try to understand what we see here. So this slice is going through the car in Y direction, and it was made 40 centimeters away from the baseline of the midline of the car. And this is very nice because it shows you how different parts are working together, the wings as well as the floor. So first of all, we can see some things really explained. As we see the stagnation point for every wing. Here, 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 and here. And even the stagnation point on the suspension. Under the wings and the diffuser, we have low pressure. And very important, this is a pressure coefficient. This is not total pressure, that's something else. This is more or less your static pressure. And this low pressure areas are creating both drag and downforce. If you now try to understand what we could improve at the car, first of all, we see that we have some flow separations. Here, here, and here. And they are absolutely unnecessary because there is no need to have a flow separation here at the car. And this is the car of a team from 2015 or 16, which was sponsored by SumScale. And actually, a lot of things came out, which were very easy to optimize, but nobody saw about it before because there was no simulation available. We can also see that there is a kind, or here you can also see the effect of the stepped wing, because if we would use just one big wing with this shape, it would instantly separate. But due to the steps, as René explained last week, we can bring fresh new momentum into the boundary layer and the flow stays attached. Now let's talk a little bit about this modeling stuff we discussed. So first of all, I would like to discuss with you the effect of porous media and why we cannot just ignore it. So on the left side, you can see the pressure drop through the model, through the radiator, with or without porous media. And as you can see, without the porous media, we get a completely wrong pressure profile for everything which is happening inside the side parts. And this will not only lead to wrong values for, let's say, if you want to get the mass fluxes through the radiators, they will be for sure much too high if you don't have porous zones, but it will also impact the overall aerodynamics. And for this, let's take this image. Here you can see directly the effect of the porous media. So here's the radiator. You won't see it because it's just a cell zone, but you can see the effect that we have this pressure drop behind, which is not here without. And we can also see this is really changing the global flow topology at some point. So it's maybe hard to see it now at the first view, but the flow also around the wheel wing is looking different. And actually, we are underestimating the drag if we don't have the porous media in our model. Yeah, now it becomes even much more interesting because through the radiator we have more stagnant flow and more drag, but not only more drag, also now you can see it, the whole flow around the car is looking different. Let's zoom in. So again, upper picture has a porous media, the lower one not. We have a completely different velocity field inside the side pod, but not only there. It seems that now the flow is taking a complete different path around the wheel. While we have this big wake here, it's much smaller with the porous media and also like banded around. And this is something, without porous media, you will really get wrong results. The next thing I would like to talk with you about is MRF. And there was a question by Konstantinos. And here you can actually see why it's important, because if you only use wall velocity, you will only capture the effect of the rotating wheels, but not the effect that actually your part is really rotating. And if we, at this image, you can see it even better. If we don't have MRF, we will get flow separations behind the spoke. In this case, it's rotating in this direction. And as you can see, here we have this separations. And if we have the MRF, that's not happening. And this is how it should look like, and not like this. And now let's compare everything together. So left we have everything, MRF, porous media, and some other advanced concepts. And yeah, you can see the different effects. So if I don't have an MRF, the flow inside the rims is looking different. And this is also massively impacting the flow structures awake behind the car. If I don't have porous media, if I don't have porous media, again, the structure of my wake will change. But since I have MRF, again, we have the effect again of the swirl inside the rims. And if we have nothing, then you can see it's really a completely different solution field. The wakes are looking different. We have much other values. It's very important. And also, if we take a look from top, you can see like how the structure of the wake is massively changing. So if we don't have MRF, the flow around the wheel is impacted, and if we now have no porous media, it really the whole structure is changed. There are some other questions I would like to answer, which were already asked. Yes, this will, and now therefore I would suggest to continue with the Q&A. So if you have questions, just write them down. And the first one is by Paras, and he will know how much time it will take to be decently good at SimScale. He said he had already done a lot of ANSYS simulations. Well, Paras, that's a good question. I don't think it's really about becoming good at SimScale. If you want to get familiar with the SimScale user interface, and I was also using ANSYS before, it should not maybe take you then 1 or 2 days. In the case you already know about the fundamentals of CFD and you've experienced CFD user, it should not take you so much. In the case you're starting really from new, it maybe take you 1 or 2 weeks. But from our experience, since we're doing this first year in a row, the best way to learn it or to get started quickly is really to use it. Okay, then we have some more questions. Sorry guys, I just need to sort them. And also Konstantinos wants to know why we prefer to give a velocity boundary condition at the inlet and a pressure boundary condition at the outlet. Well, Konstantin, that's a very simple question if you think about it. Usually what we know about our car is at which speed it's traveling and not how big the pressure drop is behind the car. And that's exactly the point. If you would do it another way around, it would also work in theory, but then you need to tune your pressure difference as long as you have the right velocity at your inlet. And since you want to have a unique constant velocity at your inlet, you do it the other way around. Then some people ask about this tool OptiProf, if we will provide you with it. It's not 100% clear, it looks great, but we will let you know latest next week. Somebody wants to know what are the advantages of SimScale over ANSYS Fluent. Well, that's again a question everybody has to answer on its own, but in the end of the day, SimScale is a cloud-based tool, so it's not a piece of software. If you want to use ANSYS Fluent, you need first of all to get ANSYS Fluent, to download it, to get the right computer, to install it there, to set up a cluster, to find visualization infrastructure, and this is a big mess. And with SimScale, you can simulate from everywhere with every computer. Okay, Konstantin has another question. He said he didn't understand why MRF is the correct way to model the tire rotation in the end. Okay, give me another try, Konstantinos. Well, the point is the following. Your reels are rotating in reality. In your simulations, they cannot rotate, or if they would, it would be a big deal to create a simulation with rotating meshes. And So we want to add the physical effect a different way. One thing we can do is to add rotational velocities on the walls, but this will not add the momentum inside the rim. And to add this momentum through the rotation of the rim itself, we define a zone, an MRF zone, which is inside the rim, and there we will add an artificial radial momentum to the simulation. And the next question is by Jan. He wants to know if you also get 96 cores as a former student team. Yes, as a former student team you also get 96 cores, but then you have to register for the SimScale sponsorship. Alright, it seems like I answered all of your questions. Thank you very much for being here with us. Don't forget to join for the session next week. There we will also talk more about hands-on and race car related stuff. Yes, I wish you a nice end of the week and hope to see you next week. Bye.